Hello everyone, welcome to a physical science lesson, and today we're doing something really exciting. We're going to be revising chemical change. Now, chemical change happens all around us, and you know what? One of the reasons why we're studying this is because it's such a big part of a chemistry assessment. So let's go in and see what you need to know and what you need to remember. So when we look at chemical change, we must recognize that there are different components of this chemical change. And the first thing that we will notice is we're looking at energy and change and how that relates to each other. We're then going to look at the rate and extent of reactions. We need energy to make the reaction happen, and we're going to see how that works together. Now, obviously, when we're doing these sorts of things, we can get different types of reactions. And I've listed some of them here. You get acid-base reactions, you get redox reactions, you even get organic reactions. Now, all of these also lead to some calculations, which you know we call stoichiometry. We're not going to be doing any stoichiometry today, and we're not going to do organic or redox, although these ones also link to that very special type of reaction called a system in chemical equilibrium. So those are the things that we're going to focus on. We're going to tie some ends together, because sometimes in a test or exam, you could get these concepts linked together. We're going to spread them apart and separate them and just focus on what you need to know and give you a few examples and tips and strategies of how you can best prepare for a chemistry assessment. So let's go to our first topic, which is on energy and change. And the thing that we want to talk about, which is really important, is heat of reaction. Now, there's another word we can use for this. It's called enthalpy. And you might see that coming across. We will define it. The easiest way to look at these terms under energy and change is to look at something called an energy profile. Now, I know that you are immediately saying, oh, what's an energy profile? Is that something we do in art, where we get the profile of a person standing side on? No, it's not. It's about how energy changes within a chemical reaction, and it's dealing with different types of graphs. Some people call it the hump graph. And maybe if that helps you remember it, that's good. But let's go and have a look at those energy profiles. And we can take some notes of different terms as well. So as you can see, the energy profile starts with some energy that's related to the reactants. Those are the things that we start with in a chemical reaction. So it's the beginning stuff. And these reactants all together have a certain amount of energy. In fact, this is chemical potential energy. And what happens is that during the course of the reaction, for different substances or different molecules, they'll have different amounts of energy. The energy changes. They don't all react at the same time. So during the reaction, the energy suddenly increases. The potential energy increases. So there's an absorption of energy, and they reach this strange state here called an activated complex. And then there's a release of potential energy, and we get products being formed. Now, that energy profile is describing certain energy changes, as we can see as we move across this course of reaction. Now, remember, as I said to you, it's not time related, because molecule A might react with molecule B at the beginning, but 10 minutes into the reaction, you might get molecule X reacting with molecule Y, and it's going to follow the same pattern of energy changes. And so this is an overlapping energy picture of what's happening to all the molecules as we look at the course of reaction. Overall, at the end of the day, all the reactants are going to form products in most chemical reactions if we've got enough things going on, if we have an excess of one and there's no limiting reagent. Let's just have a more careful look at this energy profile. and we recognized that one of the key features was the heat of reaction, or enthalpy. Now, the heat of reaction is recognizing here as a definition. It's the energy that is absorbed or released in a chemical reaction. Now, if we want to be exact in terms of calculating this, it's the energy of the product minus the energy of the reactant. So let's go and look at that same energy profile and see what we've got here. So now let's go and apply this idea of heat of reaction to the energy profile and see exactly how we label it on the energy profile. So here you go. You can see we've got the energy of the product, which over here is quite low. So it's a small number. Whereas the energy of the reactant is a bigger number. It's big. So if we take the energy of the product and we subtract the energy of the reactant, over here you've got a small number minus a big number. That means that you're going to make this a negative number. And that's quite clear. The difference between the energy of the product and the energy of the reactant is this little bit shown here. And it's given the title of delta H, because that's the symbol for heat of reaction or enthalpy. Now, in this case, we've shown why it's a negative. There's a very important term for that. We need to recognize when it's a negative delta H, then it's an exothermic reaction. Why do you think it's the word exothermic? Well, exo means giving out, like exit, and thermic means heat. So exo, out, heat going out. And that's exactly what's happening here. If you look at the amount of energy that is released, the energy released from the activated complex all the way down to the product is much bigger than the energy that is absorbed. So in any reaction, we have energy absorbed and energy released. Overall, in this reaction, there's an overall release of energy. And that's why we could make that definition of heat of reaction as the energy that is either absorbed, the net energy, if you like, that's either absorbed or released. In this case, the net energy was released. But what about if it was absorbed? Well, let's go and just clarify that we've got this right. Exothermic reactions, where the energy is given out, so that's released. Those are ones that release energy. Delta H is less than 0. But as I said, you can get ones that are absorbed. And here we've got them. They're called endothermic reactions. And notice what's different here. The energy of the product is now big, and the energy of the reactant is small. So the difference between these two is going to be positive. Okay? So this is a positive value. So when it's endothermic, we get a positive value, and we can see that the net energy that is absorbed is this amount. So that's how we define your heat of reaction. We're recognizing the difference between endothermic, exothermic. Let's just get the definition for endothermic very clearly written down for a minute. So endothermic reactions are reactions that absorb energy, and the delta H is greater than 0. You can, instead of saying heat of reaction, you can say delta H. It's fine. It's just a way of summarizing it, and we all know what that means. You can use those terms interchangeably. Right, let's have a look at one or two more terms. So activation energy is a thing that we've seen on the graph, but activation energy is the minimum energy that's needed for a reaction to take place. So if we look carefully, you'll see that that's the energy that is absorbed between the reactant, between where we have the reactant and this thing called the activated complex. And so it's very important also to define activated complex. But to do that, I want to just stop for a second and deal with collision theory. Now, collision theory is something that we use to explain what's happening in a chemical reaction. We're saying the particles, they could be atoms or molecules, so I'll just call them particles. They could be ions as well. The particles of the reactant, they are moving around either as gases or as liquid, as ions in solution. They're moving around. They have energy. So because of the kinetic model. And what we're saying is if the reactants move around enough and with enough energy, they will collide with each other and they will gain potential energy. They've got enough energy. As they come close together, they increase their potential energy, they collide, they form an unstable complex, an unstable state. If they get a favorable collision and everything works out, they've got overlapping electrons and new bonds form, old bonds break, then what we will get is products will form. But the in-between state between reactants and products is known as the activated complex. So when we think about this reaction, we're thinking about little molecules colliding with each other, and initially they have low potential energy, but as they get closer to each other, it's like them being pushed in a magnetic field or an electric field. Their potential energy increases, and over here they actually form an unstable pair. And that unstable thing can fall apart to become what it was or to become something new, a new product. It is important to understand that there are these movements and energy transfers that are happening. And the in-between state is the activated complex. So we define an activated complex as an unstable transition state from reactant to product. I think you've got that very clearly sorted out. Now, one of the things that can help us reduce the energy that's required to make the activated complex, in other words, to reduce the activated energy, to make less energy of it, is the addition of a catalyst. You say, what's a catalyst? Well, maybe you remember it, and maybe you've even heard it before. We hear it in adverts, we call them enzymes, and we recognize that things go better when we've got these special chemicals around. They serve a special job. A catalyst is a substance that increases the rate of a chemical reaction without itself undergoing a permanent change. And it does this by lowering the activation energy. And I'm going to write the shorthand for activation energy as EA there. So have a look now. You'll see there's the activated complex. Lots of energy required to get there. But if we add a catalyst, there's the activated complex. The activated energy, which was all of this, is now being reduced, and we've only got to put that amount of energy. So you can see it's a much better idea to work with a catalyst, because a catalyst gets things done with less energy. And because of the less energy, there are more effective collisions that are taking place in the same amount of time. If we've got more effective collisions, we're going to make more products. And as we're going to see just now, that's going to mean that the rate of reaction increases. So I think we've summarized really quite well the ideas of energy and change. I want you to make sure you learn those definitions, the key words that we've gone over, and the energy profile is really important. So make sure you consolidate your revision as you're doing that, and practice drawing energy profiles, recognizing what's going on, and I'm sure that these easy marks will all be yours in the bag when you do your test or exam. I think it's time to take a short break, and then we'll be back to look at rates of reaction. Welcome back, everyone. I hope you've got all your bits and pieces together. You've got a piece of paper and you've got a pen and you're taking notes and you're reminding yourself of all these important factors as we're revising chemical change. Let's have a look what we've done so far. We have dealt with the terminology and the concepts that are involved in energy and change. We're moving on now to rate and extent of reactions. These are very closely linked together, and some of the terms are going to be overlapping. But let's go and see exactly where we're at. We know what reactants are. Those are the things that you start with. We've seen that on the energy profile. We know what products are. Those are the things that you end with. Here's an important word, the word yield. Now, it doesn't often come up, but it's important to recognize it's different to rate. Yield is about the amount of product. We can even do calculations about the percentage yield. We're not going to do those today. But I want to differentiate between yield and rate. Rate and yield are not the same. Yield is the amount of product. Rate is the time it takes to make the product, or the time for the reactants to be all used up. So there's a slightly different distinction between rate and extent. The extent in the title of this section is about the yield. The rate is about how quickly or slowly we can get the process done. So rate of reaction or reaction rate is clearly defined. And so we define it as follows. It's the change in concentration of reactants or products per unit time. Now, it doesn't only have to be concentration. It could be the change in mass or the change in volume of either reactant or product. But the most common way to define it is in terms of concentration. And in fact, there's a formula for that. And I want to just write the formula down quickly and say to you, rate is going to be the change in concentration over the change in time. And so remember that this change in concentration over change in time is going to be the gradient of a graph. And we're going to look at one that comes out towards the end of this lesson, or the segment at least. So bear that in mind as we go on. Now, reaction rate is linked to collision theory. Remember, we've spoken about collision theory. It's that theory in terms of the molecules or the particles of a reactant moving around, bouncing into each other, colliding. Now, very important is the conditions and the requirements for that collision to be successful. Those molecules need to have enough energy. Usually, that's kinetic energy. As they come closer together, that kinetic energy is converted into potential energy. But they can't have too much kinetic energy because then they'll bump into each other and they'll collide off. We don't want that to happen. So they have to have not too little energy because the electron clouds would repel each other if they had too little kinetic energy. They mustn't have too much because then the nuclei of the atoms would repel each other. They've got to have just the right amount. It's called the Goldilocks factor. Just enough energy for them to overlap. On top of that, they've also got to have the correct orientation. What do I mean by that? It means that if we have a p orbital that's going to overlap with another p orbital, then these two p orbitals are going to have to be in the same direction. There can't be the one p orbital sitting here and the other one like that. Now, on top of that, those p orbitals have to have one unpaired electron. And it's only then that we can get a successful covalent bond. So please remember, enough energy, correct orientation, and that orientation means that the orbitals have to overlap in the correct way. And they have to overlap with the unpaired electrons in those half-filled orbitals. Very important. Now, the factors that we are going to look at are recognizing that we can increase the rate of reactions when the number of effective collisions increase. And the effective collisions are going to increase when we have the right amount of energy and correct orientation. Now, what can determine then to get these effective collisions? Well, there's some things that you're going to need to list, and you must learn these factors. So let's look at the factors, and we'll show how they work together. The factors include the nature of reacting substances. So, for example, group 1 metals are highly reactive, where something like lead is hardly reactive, or gold, it's unreactive. So depending on the reactivity of the metal, or the non-metal, which depends really on the electron configuration, we recognize that different things can react quickly or slowly. So the type of material that you've got affects the rate of reaction. The surface area affects the reaction. The concentration also affects the rate of reaction. And when we talk about concentration, the equivalent of concentration for gases is pressure. Temperature is also going to affect the rate of reaction because temperature is related to the average kinetic energy of all the molecules together. So if you increase the temperature, you're increasing the average kinetic energy of the molecules. And we've already said, if those molecules are moving faster, they've got more chance to collide. And if that's the case, we're going to see an outcome of that. The presence of a catalyst. Well, the catalyst is there to lower the required energy to make the activated complex. It decreases the activation energy, and it usually does this by holding some of the reactant molecules in place so that passing them by, other things can latch on. So it creates a platform for this reaction to take place, which is slightly like bees around the honey pot, if you like. They're all attracted to this thing that's holding them there. If we've got gases floating around in the air, it's not likely that they're going to bump into each other. It's a bit like finding a camel in the desert. It could be anywhere in the desert, all over the place. Big area, not likely to collide. But when you've concentrated them around the oasis, then you'll find a camel that's there, and that's exactly what the catalyst does. It brings things together so that they can latch on and collide with each other. So let's look at the effect in terms of collision theory. So I want you to remember that surface area means that if you want to increase the surface area, you've got to make the particles smaller. Because there's gaps between those little particles. The more surface is uncovered. If you've got a slab or a plate, then you can't get in between them. If you crunch them down into fine powder, each of those little particles have a bigger surface area. So the bigger the surface area, the higher the rate. Small particles, greater surface area, increase rate. Now, the next one, concentration, which is pressure. If things are more concentrated under higher pressure, they're closer together, more likely to have effective collisions, increase rate. So if this is high, then you're going to have a high rate, big rate. Okay, if we talk about temperature, well, we've said it already. Higher temperature, more kinetic energy. So remember, it's directly related to average kinetic energy of the particles. That means that if you go increase this, then the rate will increase. And the presence of the catalyst we've dealt with. I've just mentioned that to you, so you've got that very clearly. Now, here's a typical question, and I just want to deal with two little aspects of this question. I've extracted just the data from an exam question, and I want you to do that yourself. Don't only look at the questions, look at the things like graphs and so on. So look here. The gradient of that graph compared to the gradient of that graph. Which one is the bigger rate? Well, you can see this one is steeper. So this one is high rate. Notice they finish at the same amount. This one finishes before that one. So what conditions do you think that are going to be in effect to make the rate higher? So to get graph A, I think it would be at a higher temperature. And what else? It might be at a higher pressure. Well, it's not, because that's liquid, so it's not high pressure. But what you could also think about, it's not more of, there could be a catalyst. Okay, so if you look at the reaction, this is peroxide making water and oxygen, and this was the collection of oxygen. So we've got the ideas very clearly seen. So use these to apply your knowledge and recognize that we can manage answering any question on rate of reaction. Now, just be clear about this. Recognize the graph could be different. If they asked you what would happen if the temperature was colder, well, you'd need to draw a graph with a lower gradient. And it might only go up to there. Right, we've done quite a lot of exploration of chemical change, but there's more to come. So take a quick break, and we'll be back straight after the break. Hello everyone, welcome back. Let's get into some more revision on chemical change. And so remember what we've done so far. We have looked at energy and change. We've looked at rate and extent of reactions. And now we're going to focus on chemical equilibrium. This is one of the more difficult parts of chemical change. And so let's make sure that we've got all the details of chemical equilibrium sorted out, because it's incredibly important that you don't get turned off or get a mental block because you're saying, oh no, chemical equilibrium, it's so hard. Guys, there's lots of little marks that you can get. So don't be put off by chemical equilibrium. It's actually very straightforward if you get the basics in line. And you know what? You'll always be able to pick up marks. You don't have to always get the big calculations correct. So let's go over the basics. The important words for chemical equilibrium are these ideas about an open system, a closed system, a reversible reaction. And then what is chemical equilibrium? Well, they're all very important ideas, and we want to try and unpack them one step at a time. Now, if we talk about an open system, what do you think about what that means? Well, it means that the stuff that's in the system can escape. It's not bounded. So it could be something like a reaction where we're producing a gas. The product is escaping. It's not all there at the end. So when we talk about a closed system, it's contained. And so we need to recognize that the conditions for chemical equilibrium are that we need a closed system. All the stuff that we started with has to still be in the container. Now, what about a reversible reaction? Well, if we say that A plus B goes to form AB, well, that could be a reaction that is happening around us. It could be something like iron reacting with oxygen to produce rust. Not very hard or not very easy for that to now be reversed. Very hard, in fact, to take rust and make iron from it. It can be done, but it's going to cost you a lot of energy. A reversible reaction is one that you can go the other way. So instead of just saying A plus B to go to AB, we can say there's a route for us to start with AB and produce A plus B. Now, not only does this reversible reaction need to be possible, but they need to take place in the same container at the same time. That's when you get a situation that could give you a state of chemical equilibrium. Now, chemical equilibrium is something where the rate of the forward reaction will equal the rate of the reverse reaction. So whatever is happening, producing a product, the products are forming the reactants. And we can put this into a graph. So the graph would look something like this, where we recognize the forward reaction is the one in red. It's coming all the way down there. And the reverse reaction is starting off with nothing at the beginning. So we recognize the reverse reaction forms, and it gets exactly the same end point. So it's at this point the rates are equal. Now, let's be very clear about this. This was an example of hydrogen and iodine reacting to form hydrogen iodide. It doesn't matter what the reactants or the products were. What we notice is that the end point is the rates of reaction are the same. So be very clear about that, and they're happening in the same container at the same time. In fact, we can recognize there's another graph here, which is a graph that is not a rate graph this time. That's wrong. It's a concentration graph. So here's the concentration, and here we've got hydrogen, and here we've got iodine, and here we've got hydrogen iodide. And what you'll see is at the beginning, they were different amounts. This one was high, this one a little lower, this one was nothing to start with. But as the reaction proceeded, the reactants, the hydrogen and the iodine, decreased, and the hydrogen iodide increased. They didn't get to the same amount, but they got to a constant. So they're parallel to the time axis. And at this point, we would say the concentrations, they're not equal, concentrations are constant. They're not changing anymore. And because of that, we would say from this point onwards, this time, they're in equilibrium. Equilibrium has been established. We can't measure the rate all the time, but we can measure concentration, and we can see when concentration is constant. Even if it was in a big container, like in a factory, you can take a sample and measure the concentration. And in that way, we can determine that it is at a state of chemical equilibrium. Because of that, we have an important indicator that is a very important thing for us to know, and that's known as the equilibrium constant. It is related to the rate constant, but we're not going to go into those calculations. We'll leave that to the university students. What we are going to do is we're going to derive an expression for the equilibrium constant in terms of concentrations. And what we're then doing is we're saying, so this equilibrium constant is known as Kc. It is always related to a specific chemical reaction. It's not related to a generic chemical reaction. So if I want to write down the Kc for this reaction, there are two things I need to know. First of all, I've got to check that all the substances are either gases or in aqueous solution. If there's a liquid or a solid, I can ignore it, because a liquid or a solid's concentration is not going to change during the course of the reaction. A solid, its concentration is related to its density. Solid's density doesn't change. A liquid's density will not change either. So that's why we exclude them. So in this case, we're lucky, it's all gases. So we're going to write the expression for Kc as follows. We're going to write it in terms of concentration. So we use square brackets to indicate concentration, and we're going to say we want the concentration of hydrogen iodide. Now, that's the product. And we're going to say, notice that there's a 2 in front of it. And we're going to make that 2 a power over there. And then we're going to say that's the numerator of this constant calculation. We're then going to say the concentration of hydrogen in the square brackets times the concentration of iodine, also in square brackets like that. And that's the Kc expression for this chemical reaction. I want you to notice clearly there are two parts to this Kc expression in this case. There is a numerator and a denominator. So recognize you've got a numerator and you've got a denominator. Not all reactions will have them like that, but in this case it's useful for us to understand there's a numerator and a denominator. And here is a little bit of maths, not a lot of maths. The ratio between the numerator and the denominator is very useful to interpret. If the denominator is bigger than the numerator, then you're going to get a fraction. If the numerator, the number at the top, is bigger than the one at the bottom, then you're going to get a number bigger than 1. And that is very useful to know. So let's go and make sure that we understand what that means. When we're talking about the difference in numerator and denominator, I need you to understand this is a constant, except when we change the temperature. If you change the temperature, the Kc can change. But it's the only thing that will change the Kc. If you change concentration, you change pressure, you add a catalyst, you're not going to change the value of the Kc. It's only temperature that will do that. So please stress that. And so now what we're saying is, if we look at that and we say, well, we've got a Kc value that is much bigger than 1. What is that telling us? It's telling us that whatever is over here, as we had it before, Hi squared over H times I2, then what's that telling of? It's bigger than 1. It means that this is big. It's telling us this is small. So what does that mean in terms of the reaction? Well, remember the numbers at the bottom are the reactants. This is telling us that the position of the equilibrium is shifted so it's favoring products. So what this is telling us, there is more product. Okay? Whereas in the other situation, over here, when this is a fraction, so at that case, we've got H2I2, and we've got Hi squared. That's telling us that this is big. When that's the case, we've got a fraction, and that's telling us we've got more reactants. The position of the equilibrium is favoring the reactants. It means initially the forward reaction wasn't so fast. And they've come into equilibrium where the rates are equal now, but there are more reactants than products. And so you must get this very clearly in your head, that chemical equilibrium doesn't mean you've got the same amount of reactants and products. You can have different amounts. And we can even move the position of the equilibrium because there's a principle called Le Chatelier's principle. And that's the thing that we are going to spend a few seconds on as we look at it. When the chemical equilibrium in a closed system is disturbed, how is it going to be disturbed? By stress. The stress could be temperature, pressure, concentration. Then the system will reinstate a new chemical equilibrium by favoring the reaction that opposes the disturbance. So we need to understand a stress causes a reaction. The system works to undo that reaction and establish a new chemical equilibrium. Please, you've got to get this very clear and be able to answer these questions. Get a system that works. Identify the stress, recognize what the response is, recognize what the effect is going to be, and then you can see what the consequence is. So the factors, concentration, pressure, and temperature, I've mentioned those, and I want to just show those to you on a graph very quickly. In this case, you will see here, graph of concentration, all of these were parallel, they were in equilibrium. But here's the stress. What's happened? The concentration of ammonia has suddenly increased. So the increase of ammonia has caused a response. look what's happened. If we increase the amount of ammonia, what does the system do? It says, hold on, we can't get out of sync, let's use it up. And so what the system does is uses up the ammonia to make more of the reactants. So in other words, the reverse reaction is favored, and what do you see? There's an increase in hydrogen and there's an increase in nitrogen. You might be saying, why is the bump so different? Well, because that's 3 parts and that's 1 part. And then what do you see? There's a using up of the ammonia decreases until a new what? At this point, there's a new equilibrium. So there's the new equilibrium is established, and we've got the system back into sync. Remember that you've got to be able to analyze these graphs in terms of Le Chatelier, and be very careful about answering these questions, not in a long paragraph, just put down the points, recognize the stress, identify the response, and see the effect, and you'll be able to answer Le Chatelier's principal questions. I think, you know what, let's take a short break, and after that, we're going to look at an application of chemical equilibrium to a particular type of reaction, those that we call acids and bases. We'll be back straight after this break. Welcome back. We're into our last little look at revising chemical change. And the thing we want to zoom in is on acids and bases. Now, acids and bases are a particular type of chemical equilibrium reaction. This is quite a big topic, and we're not going to have time to do everything because the stoichiometry that's linked to this has been done in other lessons, so we're not going to follow that. Also recognize that stoichiometry is linked to titrations. So we're just going to focus on some of the theory that's taking place in acids and bases. So there are 2 main theories. There's Arrhenius' theory and Lowry-Bronsted theory. You need to know these 2 theories. And I can almost guarantee you that one of these definitions is going to come up from one of the theories. So there are 4 things you need to know. What is an acid? What is a base? According to these 2 theories. So let me remind you that in terms of Arrhenius theory, an acid produces hydrogen ions. That's H+, aqueous, or we can say hydronium ions, aqueous. Now remember, a hydrogen ion is just a proton, because hydrogen has 1 proton, 1 electron. It's lost the electron, becomes positive, so it's a proton. And that's going to become important in our next theory. The bases produce hydroxide ions. That's OH-. In aqueous, AQ. So remember the phase indicator? AQ stands for that. That's Arrhenius' theory. Anything that produces hydroxide ions is a base. Anything that produces hydrogen ions, when you dissolve it into water, is an acid. Guys, there are some exceptions. We can find things that don't produce hydroxide ions, but they're still going to be bases. There are some things that don't produce hydrogen ions, but they're going to be acidic. And so we need to be aware of that this theory isn't complete. It needed to be replaced or added to. And so Lowry-Bronsted came along, Bronsted-Lowry, sometimes reverse those, and they indicated the following, that an acid is a proton donor. There's a transfer of hydrogen ions. Those hydrogen ions, just the protons, and a base is a proton acceptor. Now, let's go and have a look at a reaction where we can see this happening. And the most important of these reactions is the reaction that takes place between 2 water molecules. It's also known as the auto-ionization of water. So have a look here. Auto-ionization of water is the reaction of water with itself to form hydronium, that's H3O+, plus hydroxide ions OH-. So in the auto-ionization of water, particularly said that this is at 25 degrees, and you'll see why in a second. The water molecule bumps into a water molecule. This water molecule donates a hydrogen ion. And if it has donated a hydrogen ion to this one, look over here. What's happened to that one, the second one? It has become a hydronium ion. And this one, which was hydroxide, it has become, this was water, it has become hydroxide. It has lost, this one has lost a hydrogen ion, and this one gained the hydrogen ion. And so that's the process. We would say this water molecule is behaving like an acid, and this one is behaving like a base, because it's accepting a hydrogen ion. Now, do you notice that in this reaction where we've identified water is acting sometimes as an acid and sometimes as a base, is actually in chemical equilibrium? Look, we've got the double arrow there. So water molecules on this side, and we've got ions on this side. And in fact, what we can do is we can say, so what is the role of the things in the reverse reaction? Well, this hydroxide ion, if it's going to go in the reverse reaction, it's going to be an acceptor of hydrogen ions, and that means that it will be the base, and in the reverse reaction, this will be the donator, so this is the acid. And there's a fancy name for this. In the reverse reaction, we call them conjugate. So that's the conjugate a base, and that's the conjugate acid. And they form a pair. So what we need to recognize here is that the acid and the conjugate base form a pair, and here's the other pair. The base and the conjugate acid form a pair. Now, it's not that easy to see on this example. We'll come to another one. But I want you to recognize, because it's in chemical equilibrium, we can write a Kc expression for this reaction as well. But remember, we must only use those things that are in aqueous or gases. So that means that if it's liquid, we can ignore it. So if we write the Kc expression, it actually turns out to be this expression here, which is also called Kw. And it's known as the ionization constant of water. Ionization constant of water. And what's quite nice about this is at a particular temperature, and it has a value. Remember, that value is not going to change if the temperature doesn't change. So if the concentration of the hydrogen ion increases, for example, the product still has to be the same. So the hydrogen ion concentration increases, which means the hydroxide must decrease. If the hydroxide increases, the hydrogen ion must decrease. The product of the two have to always be the same. And so we recognize that no matter what, the Kw remains the same at that temperature. And this gives us an opportunity to define what pH is. In fact, pH is just a log equation of what we've just seen of the Kw. All we're saying is that at a neutral situation, the hydrogen ion concentration is equal to the hydroxide ion concentration, and that means that this will be equal to 1 times 10 to the minus 7. And if you multiply that together, then you'll get 1 times 10 to the minus 14. So by looking at the log of the hydrogen ion concentration, the minus 7 becomes 7. So it's actually quite intuitive in that respect. You can do lots of calculations on these. As we've shown, the water is an amphiolite. It's a substance that can react either as an acid or a base. There are other amphilites, but water is the most common one that we will look at most often. Here's the thing that we do need to get into. What's the difference between a strong acid and a weak acid? Well, a strong acid ionizes completely. It has a high concentration of hydrogen ions. And a weak acid will be one that doesn't ionize completely. It will rather prefer to stay as molecules, and only a low concentration of hydrogen ions. So the pH will generally be a bit lower. So the acid ionizes completely, and in this case, as I said to you, we're going to see that we've got, this is the acid, and that is the conjugate base. Notice that they differ only by the hydrogen ion. Now, for a base, the strong base dissociates completely, and we recognize something like sodium hydroxide forms hydroxide ions and sodium ions like that. So in acid-base reactions, final thing that I want to get to is that an acid plus a base gives you salt plus water. And that reaction and the balancing of those equations you need to know. But there's one other thing. When it gets salt and water, sometimes the salt can react with the water. We call that process hydrolysis. Please learn that definition because it's very important. You have to define hydrolysis, and we define it as the reaction of a salt and water. So when you come to a titration, the salt may react with the water and the end point might not be neutral. And that's why we've got to choose the correct indicator. Guys, that's just been a quick revision of all the important concepts of the theory of acids and bases. Please do some more practice and make sure that you understand these are all related to chemical equilibrium as an example. So I wish you all the best for your tests and exams. Hope you found this useful, and I will see you soon. Bye for now.